Okay, today we're going to expound upon our separable differential stuff and bring some word problems into it. You've done these types of problems before in pre-calculus. We're just going to add a calculus twist to it. Most of this stuff you'll be doing just like you did in pre-calculus, but because it's calculus, you need to understand where it came from. So I'll show you one of those, and then we'll do one without it. That doesn't make much sense until we get into it and you understand what I'm talking about. So we're talking about growth and decay, exponential growth and decay, which normally is not a very positive topic because it deals with things like the spread of disease, the zombie apocalypse, radioactivity, that kind of non-happy stuff. But I do have one at the end that's a little bit more uplifting. So today you should be able to understand the Pert equation. You've heard of that before, right? No? How many people have not done this in pre-calculus? Ooh. Oh, this will be fun then. Okay, good. So then by the end of the lesson, you should understand the Pert equation. We're also going to talk about, as I mentioned, using calculus to derive the Pert equation, because last year in pre-calculus, you were just given this magical equation and you used it to solve a bunch of problems. In here, we're going to talk about where it comes from and how you get it. And then most importantly today, you should be able to believe in yourself, as I believe. A little bit of self-love today. It's Monday. Okay, so for those of you that have never seen this before, this will be good because I got a little bit of review. This is what's called the Pert equation. That's the proper way to write it, even though we shortened it to Pert equation. P is the final amount. So if we're talking about something like radioactivity, it's the final amount of radioactivity you have. P naught is the starting amount. And this has application for all kinds of things. E is just plain old E. Anybody think they can fire off the number E?
2.18.
No.
2.71.
You don't remember what I did with the 29.
2.7182.
All right, keep going.
Oh.
You're good so far. 2.71828.
1828 again.
Yup.
That's disgusting that you know that.
It's the I forgot the rest.
Last six?
45, 90, 45.
Perfect. 45, 90, 45. Okay, so that's E.
Okay.
R is not a pirate's favorite letter. Pirate's favorite letter is C. Good. That's the growth or decay rate. And then T is time. Down at the bottom left, y equals c times e to the kt is another version of the exact same thing. That one's a little bit more calculus friendly to us because c is a constant, and for some reason we're going to change r to k, a growth rate or a decay rate, and then t is always time. However, on the right-hand side is something that you never talked about in pre-calc because that's a derivative. Now, the way that would be read in English would be the rate of change of y over time is directly proportional to the value of y. And this may all sound like gobbledygook, and hopefully it'll make sense when I start diving into the examples. So for those of you that said you've never seen this before, do you still feel that way, or is it starting to come back to you? Still feel that way? Okay, that's okay. That's what makes this such a great country. All right, so let's start with some bacteria. Better a bacteria than a virus. Okay, so we've got some bacteria. And I'm starting with 600 bacteria, and 2 hours later, all of a sudden, I've got 1,800 bacteria. It's the spread of disease. Anybody in AP Bio? Do you do this at all? No? Okay, good. We're going to take this one from start to finish using calculus. The next one we will just do using pre-calculus. Okay. I'm going to start with this sentence here. The rate of increase, well, I need a variable. I'm going to have B stand for the bacteria. Number of bacteria in an equation. there's no reason to write this, but I'm going to anyways. T is time. The rate of increase, it's implying that it's the increase of bacteria, dB dt is directly proportional to the number of bacteria present. KB. Kobe Bryant. Moment of silence. That was a silence. Okay. So K is an exponential, is a proportionality constant. It's some number that multiplies it by the other number. We have no idea what it is. We'll find it eventually. Are you good with that equation?
Yes.
I got one yes, it's good enough for me. That's a separable differential equation. We've done it already. How do I do it? What do I do first? Yeah. Well, I'm going to do two things. I'm going to do this and, whoops, that. In other words, I'm going to cross multiply. Now, I could take the K with the B, but it's easier if you leave it where it was. So I'm going to leave that proportionality constant on that side. All the B's and the dB's are on one side. All the T's and the dT's are on the other side. What's next? Say it again. Integrate. Left side's easier. We'll do that first. What's the antiderivative of 1 over B? Correct. And we can drop the absolute value because B is going to be a positive value because it's the number of bacteria, so it can't really be negative. That wouldn't make any sense. Way back when we started integrals, I said that little dx or that dt or that dy in an integral was extremely important because it told you what the variable is. So on the right-hand side of that equation, what's the variable, k or t? T, good. So what's the antiderivative of k dt? Kt, very good. Not 1/2 k squared. Kt. We're all good so far? Yes? How do I solve that for B? Yeah, we do the e to the raised to the e trick. Please tell me you all know that, yes? Yeah. Oh, I forgot something. That's kind of important. And I'm choosing to put that C on the side with the T because it makes our lives a little bit easier. Go ahead.
So the plus t when you raise to the plus t stays for the kt, it doesn't move out. It doesn't eat the
Not
kt
yet.
plus t.
It's coming.
Okay.
Yeah. Because I'm raising that whole side as the exponent for the e term. Okay. What's the left-hand side become? B. Yeah, they just cancel. E to the natural log of anything is that anything, so the left-hand side is B. That's easy. Okay, now before I ask you that question, I'm going to ask you this. What's that equal? X to the fifth? Or X to the sixth? Fifth, you sure? Okay, good, just checking. That's going this way. This problem is going to involve going the other way. So I'm going to rewrite this as e to the kt times e to the c. What's e to the c? C. Right. No matter what we do, a constant is still going to be a constant. Get rid of this mess over here because you knew that. And bring this puppy up here. So we get B. The number of bacteria is equal to C e to the kt. That's the Pert equation. Just with the variables changed a little bit. C is our starting amount of bacteria. K is the growth rate, because this is a growth, it's getting bigger. T is time, and B is the number of bacteria. So that's the calculus. We're done with that. Now we're going to do some pre-calculus, which involves plugging and chugging. Are you good with this?
Yeah.
Can I erase?
Yeah.
Okay, because I need more board space here. Does that little dot bother anybody? No? Good, I'll leave it there then. We'll see if it doesn't bother anybody. Okay. 600 bacteria grow to 1,800 bacteria in 2 hours. In this equation, there are a number of things I need to know. I need to know how much bacteria I started with. What's C? 600. Yeah, we started with 600. So this would be B equals 600 e to the kt. What I really want to find is K. I want to know what the growth rate for this bacteria is. And if you don't remember, I will tell you this, that if K is a positive number, it's a growth. If it's a negative number, it's a decay. This is a growth, so we should get a negative, or sorry, we should get a positive value for K. Okay, so what do I know? Where do I go to from here? How do I use this to solve for K? Go.
You can plug in 1,800 in 2 hours.
Love it. Perfect. I will have 1,800 bacteria, starting with 600 bacteria after 2 hours. Well done. I cannot stress this enough. You must store values when doing exponential calculations. We will get a value for K and approximate it, but when you're doing the actual calculations, you need to store it. And I'm going to do this one with you just to make sure there's no mistakes. What do I do next to solve for K? Say again?
Divide by 600 on each side.
There you go. Now what?
Natural log.
Yeah, now we take the natural log of both sides
Divide by 2.
and divide by 2. Whoops. So K is equal to the natural log of 3 divided by 2. Okay. I'm going to leave it like that, but I'm also going to ask you for an approximate value. What is that about? Somebody tell me what that's about equal to. Maggie? 0.54. Give me 3 decimal places. 549. Thank you. This is no good to me. Even though it's 3 decimal places, it's not going to be accurate enough for an exponential equation. So you should store that number into some variable. Oh, I don't know. Store it into x, store it into k, whatever you need. Which means that I can then take this a step further, and we would know that we get this. There's my final equation for this bacteria problem. Knowing that equation, there are only 2 questions I can ask you. What are they? Good. Those are actually 2 questions wrapped up into one. After X amount of hours, how much bacteria do I have? Question number 1. Question number 2, if I have this much bacteria, how long does it take to get that much bacteria? Part B of this problem says how much bacteria do you have after 4 hours? So do the calculation. Put 4 in for T and tell me what you get for B. B is equal to 600 times that value that you stored times 4. Be careful with parentheses. B is equal to get out your calculator. F for the semester. Anybody else want some? Page, calculator? F for the semester. You can have an F plus. I like you more than him. Beautiful. 5,400 bacteria. The word problem should have a unit on that. Questions? Okay, the next one, which involves radium, we're going to do without deriving the Perb equation. We're just going to start plugging and chugging. Who's an AP Chem? Tell me about radiation. Tell me about radium. Tell me about half-life. What do you know? No pressure, though.
Half-life equals natural log of 2 over K. That's about it.
What? Okay, so imagine you're sitting at dinner with a 10-year-old cousin. How do you explain half-life to a 10-year-old?
It's like the amount of time it takes for like something to decrease by half its energy.
Perfect. Everybody good with that? You all knew that, right? Yeah, I do. Xana's such a great teacher. Yeah, it's the amount of time it takes for half of the material to just disappear. So if I have 50 milligrams of pure radium, after 1,600 years, I'll be left with exactly 25 milligrams. It just dissipates and goes into the atmosphere, breaks down. But before that, you said something else, Anna. What did you say that half-life was?
Natural log of 2 over K.
Why? Do you know? Well, I'll call it. No, hold on. No, I don't mean to keep putting you on the spot. Do you know where that comes from, or were you just given that formula? Say, here, go memorize it.
We're just given it.
Okay, so let's talk about where that comes from. Let's suppose I start with R naught. I start with some amount of radium. It could be 50 milligrams, it could be 3 tons, it doesn't matter. 1,600 years later, how much will I have? If I started with 100 tons, 16 years later, I would have how much? 50 tons. If I start with R naught, how much will I have after 1,600 years? Good. 1/2 R naught, and this would actually be 1,600 K. Just like in the previous problem, we would start by dividing by R naught. Because we know it's not equal to 0, we have some amount of radium. We would get this. Then we do the natural log trick. So I actually cheated because we know the half-life. This would be our T value. And we would get natural log of 1/2 divided by K would be equal to the time. Now, did you guys learn it's natural log of 1/2 over K or natural log of 1/2 over R?
Natural log of 2 over K.
That's not right. That's a doubling time. Ooh, that's a good segue, though. Okay, so this is a half-life problem, which we already talked about. There's also something called a doubling time. Doubling time would be the opposite of a half-life. For instance, if you have a bacterial growth, the doubling time would be the amount of time for the number of bacteria or the virus to double. It's very common in investments. You graduate from high school, you get $2,000 from your family. How long will it take for my money to double? A half-life would be a natural log of 1/2 over K. So I don't know what kind of mucky muck they're teaching you there. They're teaching you a double. None of that matters to us. All of this was just a reason to show, or an explanation as to where that thing comes from. We're going to start from the Perb equation. And we're just going to plug in what we know and solve for what we don't know. So what do I know in this case? I know that I'm starting with 50 milligrams. I don't know the decay rate, but I do know it's going to take 1,600 years for me to end up with 25 milligrams. So no calculus, just dive right into pre-calculus. And then solve it. Okay. So we did this already, so I'll just skip to the fun part. The natural log of 1/2 divided by 1,600 will equal K. Plug that into your calculator, everybody, and tell me what that number is. First of all, is it negative? Good. What is the number?
Negative 4.3332.
There's more to that.
Times 10 to the negative 4.
There you go, times 10 to the negative 4. That's the important part. This number is actually negative 0.0004, was it 3? You said 332 or 322?
332.
332. That's a really small number because it's taking 1,600 years for that stuff to disappear. And that's also why you want to store that number to get it as accurate as possible. So you all know what Chernobyl is, right?
Mm-hmm.
Okay, so can somebody summarize what happened at Chernobyl? Cindy, go ahead.
A nuclear power plant exploded.
Mhm.
There's radiation
Everywhere, right. So that happened in the late 70s, I believe. And we still can't safely go into that area. So what scientists are doing on a regular basis is calculating when is it going to be safe for us to go back into the area. There's researchers going in there, but they go in heavy radiation suits and that kind of stuff, unless you're playing Modern Warfare. Right? Is it the first one? Does anybody know what I'm talking about? Christian, you should know. You're playing Modern Warfare all the time. Is it the first one when you go to Chernobyl?
I don't know.
Don't pretend you don't know.
No, I
You know.
actually don't.
Liar, liar. All right. Anyways, we know through research what a tolerable level of radiation is for human beings. You're being bathed in radiation right now. The sun's shining in the windows. There's fluorescent light shining on you. Certain levels are safe. When it gets above that safe level, obviously it's going to cause a problem. So they know what levels are safe for Chernobyl. So somebody sat down and done this calculation, knowing how much radiation was released at the meltdown point, and the calculation is astronomical. It's a couple hundred years before we can even begin to come close to going back into that area. Okay. So we know now that I can take this K value and come up with my general equation for this particular problem. The amount of radium that would be left over would be 50 times e to the negative 0.0004332 t. Okay. So let's suppose this is the equation for Chernobyl. It's not, but let's pretend it is. When will the radiation level be 0? Go ahead, do the calculation. Set R equal to 0 and solve. Why you eyeball me, son? What are you thinking? Why?
Because e to the something is always something.
Good. Everybody follow? Okay. There's two answers here. Well, there's a number of answers, but here's a couple different ways to look at it. If you go out today and you mow half your lawn, and then you come out tomorrow and you mow half of your lawn, and then you mow half of the lawn, when will the lawn be mowed? Never. You can't do it. So if radium is disappearing, half of it is disappearing every 1,600 years, then half of half disappears, and half of half disappears, and half of half disappears, and it never disappears. You can't have 0 radium at that point in time. That's the logical approach to the problem. The mathematical approach to the problem, like Tom said, is to do this. Divide by 50 and then take the natural log of both sides. And you can't take the natural log of 0. You try to take it on your calculator and it gives you an error because remember the natural log. Yeah, you can only take the natural log of a positive value. Okay. Once we get that stuff in the red rectangle, we're back to the same two questions we've talked about. Here's how much radium I have. How long did it take to get down to that amount? Or here's 10,000 years later, how much radium is left. Okay, we good? So we have a growth problem, we have a decay problem, and now we have a Newton's law of cooling. Do you do this, Kim?
Not yet.
Anybody know how cooling works? Thermodynamics?
Oh, yeah.
Tell me about it. What do you know? You're like the shell answer woman today.
I mean, the energy's still there, but it's just not in whatever you're.
Okay, so let me hear. This might be easier. I leave the room and I come back with a Venti blonde Americano. It's 198 degrees. I bring it into this room. Let's say it's 75 degrees in this room. What's going to happen?
The energy's going to be transferred to the room.
Okay, that sounds great, but what does it mean to a 10-year-old? What's going to happen to the coffee? It gets colder. What happens to the room? It gets warmer. Which one is more noticeable? Yeah, the coffee getting cold. The room will warm up, but it'll be a small amount of difference. Isaac Newton, remember we talked about him, he's the idiot that invented calculus and was very mean and ruined that other guy's life. Created a law of cooling. This one is a little bit different to set up and requires a little trick to solve it, and that's why I wanted to do it with you. According to Newton's law of cooling, the rate at which the object cools is directly proportional to the difference in temperature between the object and the surrounding medium. So the surrounding medium would be the temperature of the room. So I've got some coffee that goes from 125 to 100 degrees in a half hour. When surrounded by an air temperature of 75 degrees, find the temperature at the end of the next half hour. All right, let me see what variables I used here. I used y to represent the temperature, because I've got t already for time, so t is time. Okay, and I get this. The rate at which the temperature changes is directly proportional to, so that's our proportionality constant again, the difference between the temperature of the object and the temperature of the surrounding medium. Okay. So that's a little bit different than what we've seen, because now all of a sudden there's a difference in there. And when you solve it, the struggle comes about when you try to solve it, because what people try to do most commonly, if I just said to you, here, go solve this, I would guess you would probably try to distribute the C. And then you got this 75 times C term, which causes a whole bunch of hurt. So we're going to do it an easier way. I'm still going to cross multiply, but I'm going to treat this thing as one unit. So it becomes 1 over y minus 75 dy is equal to C dt. As we've done before, we integrate. Let's do the right-hand side first. What's the integral of C dt? CT. And then this guy, what's the antiderivative of 1 over y minus 75? Yeah, natural log of y minus 75. Okay, so let's, another sidebar here. Do I need the absolute value bars? If I bring 198 degree coffee into the room, and the room's 75 degrees, can the coffee ever get colder than 75 degrees? No. Everything in the universe strives for equilibrium. Therefore, that value cannot be negative, so we don't need the absolute value bars. We're just going to use some parentheses here. And most of the time in these problems, you won't need the absolute value bars because you can't have negative values. If you go back to the bacteria problem, you can't have negative bacteria, so we didn't need them. You know what? This is a little confusing. So I'm going to make this a K instead of a C because I need a plus C there. I need that constant. That way we don't have like a C1 and a C2. Everything else is the same. So y minus 75 is equal to C e to the kt. Was that too big of a jump, or are you with me? Did the E2 trick, e to the natural log of y minus 75 is just y minus 75. E to the kt plus c is just c times e to the kt. Okay. Now we got to play with some numbers. I know that when what do I know? An object cools from 125 to 100 degrees in a half hour. Let's see. 125 would be that. So I know I'm starting with 125 degrees. 125 minus 75 is equal to e to the k times 0. And this is a little bit different than the Pert equation because this technically isn't Pert because we got that minus 75 in there. But what I did is I used my initial conditions. I'm bringing that cup of coffee into the room at 125 degrees, and that happens at t equals 0. What's e to the k times 0? 1. 1. Oh, I forgot the c, I'm sorry. Sloppy. There we go. So c is equal to 50. That doesn't mean that I started with a 50-degree cup of coffee. That means that that starting value for that equation is 50. So y minus 75 is equal to c times e to the k. Whoops, not c. Come on, Reedy. 50 times e to the kt. Then I know, and now the one calculation I don't know now is k. But I do know that when t is 0.5, y is equal to 100. Plug and chug, solve for k. Will the value be positive or negative? Which one? Why? Or remember, k is the growth rate or decay rate. It would be negative because decay. Okay. And I'm not going to finish the problem. You can calculate that. It's not that difficult. You get your k value, which gives you your final general equation. Then you would plug another value in for t and so on. Okay, but again, that one gets a little bit weird because you've got the y minus 75 on it. Questions? We're good? So those of you that said you've never seen it, you still haven't seen this? Wow. Talk to your pre-calc teacher.
I think we did it in
That ain't-
algebra 2.
What's that?
I think we did it in algebra 2.
Algebra 2, you saw this?